Okay, we are live. So today, what's on my mind is this really interesting article about Python that I've been reading, and it's from this open source book called 500 Lines or Less. And the article is called "A Web Crawler with Async I/O Coroutines," and it's written by Jesse Drew Davis and also Guido van Rossum, who is the creator of Python. So I thought this article was fascinating, and what I want to do is to kind of think through it and try to explain it verbally by going through the article itself and having me kind of verbalize what I'm thinking and kind of guiding through the code as well. So hopefully those of you who are curious about this concept will find it useful to both read the article itself, which is actually quite long, and then also, watch me kind of go through it. And obviously in the ideal world, my audio would be synced with the document, but in this world, I'm just recording my screen in a video, and maybe someone can, cut this up later or something. Okay, so what this article is trying to convey is the challenges of writing code that needs to run a bunch of things efficiently, kind of in parallel, quote unquote. So the traditional way to do this is with a multi-threaded model, right? So multi-threading means you have one program running, one process running, and it spawns multiple threads, and each thread has its own call stack, has its own instruction pointer, has its own control flow, and they might share some variables, some shared global variables that they might have to manipulate. And then in order to do that, they have to acquire locks and synchronize the access. Otherwise, you get race conditions and other bad things. So why would you want multi-threading? It's because you have, say, a bunch of CPUs and you want to take advantage of them. Or if you have events that take a while and you need to wait on it, so that you want other threads to be able to run kind of concurrently. So this example they use for the running example throughout their whole essay is writing a web crawler. So what a web crawler is at its very simple level is you define a function. So here's, this is all in Python, by the way. So you define a function called fetch, and you give it a parameter that's a URL. And what you want to do as a web crawler is you want to grab the contents of the page at a certain URL, so a web page, and then you want to parse that page and find all the HTML links that the page is linking to, and then recursively call fetch on those URLs, fetch those pages, and then keep going until you reach some limit. So, one typical use case of a web crawler is if you want to download the contents of an entire website. So say you went to my web page, pjbovine.net, and for some reason you wanted to save all of the articles I have on my website offline for your perusal later. You could go to my articles page, click on each of the individual articles, and then download them manually, but that would be really tedious. So instead what you want to do is you want to write a web crawler that, say, goes to my homepage, downloads the homepage, then finds all the hyperlinks on the page, effectively clicking on them, fetching those pages, downloading those pages, then clicking on all of the links from there, downloading those pages, and then keeping on clicking and recursing until you've, stabilized somehow. So the simplest way to do this is by simply writing a single threaded application, right? So let's say you had a fetch function that takes a URL. At the lowest level, what this does is that it opens a socket, it creates an HTTP request, and then it sends that request through the socket to the website. So this is querying xkcd.com. So you can imagine querying my website, pgbovine.net, with this socket if they so choose. Whoops. And then it sets up a buffer to start receiving messages. So in this case, due to how this code is set up, the messages come in 4 kilobyte chunks. And then while the chunks are still coming in, you're going to append to this response binary string. And then at the very end, once you finish your response, This should be the contents of a web page. Then you call this parse links function, which magically takes the response, which is a HTML file like this, and finds it, parses it, and gives you all the links to other URLs. And then you add it to some queue, which is maybe some global queue, and then you recurse and you call fetch again on basically everything in your queue. And you keep on doing that until supposedly your queue is empty. Okay, so one problem right here, I mean, it's not really a problem, but it's an inefficiency, is that this is a single threaded application, right? This application, when you run this, when this calls, creates a socket, connects, requests, send, all of these things are what's called blocking operations, which means that it will pause your whole program until the function call essentially finishes, and then it will keep it running. So for example, this call, I mean, this call is probably really fast because it just creates a socket object locally. This call might take a little bit of time because it has to connect over the internet to a server. If let's say you're on a slow internet, this might take half a second, whatever. And then that means that your function is blocked. It can't move. The instruction pointer is right here until your thing finishes connecting. And the same thing here, the send function call might take half a second, depending on how slow your internet is. And then the most important thing is these receive calls, right? These receive calls might take a while because you're receiving data from some remote server. So again, if you're on a slow connection, each receive call might take, say, a second or something. I'm exaggerating, but you get the point. So that means that the entire fetch function, how long does it take to run? It might take, a second to fetch my entire web page or something, right? And then what happens is you add it to the queue and then you run fetch again on another web page. You go and you fetch this web page and then you fetch, I don't know, this web page and then you fetch this web page. Every time you're fetching a web page, your function is blocking and waiting until the whole web page has downloaded, and then you go on to your next page. So that's sort of equivalent to downloading a whole page, then waiting until it's done, then clicking on another page, waiting until it's done, then, I don't know, clicking on another page and waiting until it's done and stuff. And, that might be fine, but it might take forever for your whole website to be crawled because you're only doing one page at a time. But the observation is that a lot of applications, especially ones that go over the internet, are what's called network bound or IO bound, which means that most of the time, when you're in this function here, when you're calling socket.send, socket.receive, you're just sitting there. Your Python program is just sitting there waiting for the socket receive call to finish, because this socket receive call blocks your whole execution until there's something to receive, until the receiving is done or the send is done. So, but the thing is, your whole process just locks up while doing that. But in fact, there's no reason to really do that, because you can imagine running a bunch of these fetches in parallel. So let's say that my queue had a bunch of links. Let's go back to this articles example. So I have, say, 300 or so articles on my website. There's just hundreds and hundreds of these links. It seems pretty inefficient to just go through them one at a time, waiting and waiting and waiting and waiting and waiting. Why not do 5 at a time, or 10 at a time, or 20 at a time, or however many you think your network connection can handle? In theory, you should be able to open a bunch of these tabs in parallel, right? I mean, I can't click fast enough, but really your web browser, what it just did was it just loaded 5 pages in parallel. It didn't wait until each one was done loading. So how can we simulate that or replicate that in our Python code? Well, the most straightforward way, like I explained in the beginning, is to use threads or a multi-threaded architecture, which means that you're going to set up some code to create a new thread, and each thread runs a fetch function call, and then they have to coordinate to add the links to this queue, this queue list or set, I guess, because it's add. And you might have to use locks and things to coordinate that. That seems fine in a way, because it seems really straightforward. Your code is super straightforward and basic, but there are a few problems with threads. One is that debugging may be hard, because again, you might get race conditions. Threads run out of order. So for example, part of one thread might be running fetch on one URL, and then another part might start running on another URL, and then you're in the middle of another part, and then it writes to this queue, and then it messes up the queue, and it's just really hard to debug multi-thread applications. You would rather try to debug a single-threaded application. And the second reason is that threads actually have a lot of overhead in terms of memory usage, and also, you can say CPU usage. So here it says that, on Jesse's system, a Python thread costs around 50 kilobytes of memory, and then starting tens of thousands of them start causing failures. So the issue is that you can't really start that many threads at once because your system might overload in memory, or some other operating system constraints you might brush up against. It's just not a good idea to have tens of thousands of threads at once, especially because of the fact that most of the time, most of these threads are just sitting there idle, not doing anything. So in these kind of web applications or network applications, an alternative model has emerged that has been fairly successful, which is called async, or asynchronous I/O. And this is an alternative to using threads.